Before getting into the details of random number generation, the algorithms, and what to do with the simulated random samples, let's walk through an example and identify some of the features that will be relevant in our problems. Let's say we have a square of side 2 and the unit circle is inscribed in the square. Let's suppose that we have the ability to generate points randomly in this square, and the red points are those that lie within the unit circle. We can count them, and the ratio of the red points to the total number of points, it's intuitive that if the points are completely random, then that ratio will be the ratio of the area of the circle to that of the square, which we know would be pi over 4. So if we are able to count that ratio and multiply that by 4, we should have an estimate of pi. And interestingly, this estimate is completely independent of the infinite series based approximations to pi that comes from calculus. So let's see what we get, and as the sample size increases, we have generated 1000 samples here. Let's see if we can get a sense of the estimate. So let's estimate pi as 4 times that ratio of number of points, and as we see here, as the number of samples increases, the estimated value reaches the known approximation for pi, which in this case is somewhere between 3.14 and 3.15. So now let us formalize what we did and see if we can get an estimate of the accuracy of what we are doing. So we start with x and y, the independent uniformly distributed random variables between -1 and +1, which is what we are generating, points on the square of side 2, and we are interested in the probability of finding these points within the unit circle. So this presents itself as a problem of a joint of a double integration, which is what you see on the screen, y going from -1 to +1 and x between the corresponding limits depending on y, and the double integration. Because x and y are independent, the joint density function is the product of the marginals, and the marginals in turn, they are each equal to half between the limits -1 and +1. So if you go through the steps, the answer is indeed pi over 4, which was also the ratio that we thought of in the previous slide. So if we are able to estimate that ratio and multiply that with 4, we should be able to get an estimate of pi. And let's now take a look at the code, the Matlab code in this case, that generated those points and estimated the value of pi. So here is the code, and it's very simple. There is a loop where the index MCT goes from 1 through n, and for each value, for each trial, we generate one x coordinate between -1 and +1, uniformly between -1 and +1. The command rand is the MATLAB command for the standard uniform deviate. So we generate one x we generate one y independently, and then compute the distance from the origin, and if the distance is less than or equal to 1, which means the point is within the unit circle, we increment a counter which is sum by 1. That counter was initialized at 0 outside of the loop, and once we are done with the n simulations, the estimated value of pi is 4 times the ratio sum over n. So this is the process that we followed. Now let us see if we can look at the accuracy of the estimate as a function of the number of samples, the sample size, which is n in this case. So this is the problem statement. We are estimating pi by counting points within the unit circle, and so this is the estimated value of pi hat. The indicator function, the truth function, it's equal to 1 if the point is within the unit circle and 0 otherwise. So it's a binary random variable, and the probability of the truth function taking on the value 1 is, as we found out in the previous slide, it's pi over 4, and the complement is the indicator function is 0, and the probability is 1 minus pi over 4. So pi hat, which is a random variable, let's find out the mean of that random variable, the expectation of pi hat. Because all the indicator functions, they are identically distributed with the same probability of success of pi by 4, we can find out the expectation of pi hat as the sum of all those individual expectations. They're all equal, so the answer comes to pi. So the estimate that we have set up is unbiased. That's good to know. Now let us see how that is affected by the sample size, because that's the kind of thing we will do a lot in this course, that we are going to find out some probability or some other function of a set of random variables, and we would like to know how accurate that estimate is. So the variance of the estimate pi hat would be the sum of the variances of the individual indicator functions, and that's because we make use of the second very important property of the samples, that they are mutually independent. So we can just add the individual variances and multiply the sum with the coefficient 4 by n whole squared. So once we put in the values of p and q, the variance of the estimate is found to be a constant divided by the sample size. So as the sample size increases, the uncertainty in the estimate does indeed go down, and in the limit it equals the estimate equals the true value of pi, and this, as we remember from our previous lecture, that this is indeed the strong law of large numbers. Now let's see what would happen pictorially to the estimate in terms of the sample size. The movie that we saw, that had just one sample size of 1000, just one realization, one set of samples. Here we have sample sizes going from 10 all the way to 100,000, and at each sample size we are repeating it 30 times. So when there are only 10 samples, you see there are 6 possible values that have come up in these 30 repetitions, which basically means that of all the 11 possible values, there could be only 6 were encountered. When the sample size increases to 100, you can see the scatter reduce significantly and kind of assume values around the true value of pi, which is 3.1415, and so on. And as the sample size increases, the scatter indeed comes down. You can see for 1,000, for 10,000, and when it's about 100,000, all the 30 samples, all the 30 values of the estimated pi are quite close to the true value, which is also the mean in this case.